Welcome everyone to the second part of this week's lecture. So like we said earlier, pinhole cameras can focus light well, but because the pinhole is small, only little light will get in on the image, which typically be dark and dark. So over a short period of time, only a few photons will hit each point on the sensor, so the signal at each point will be dominated by random fluctuation. So we were going to try then to use a lens system, which is a single piece of transparent tissue in the eye, and the system of multiple lenses in the camera. So we can see in the drawing here that light from the tip of the camera spreads out in all directions. So the camera or an eye with a lens captures all the light that hits anywhere on the lens, which is a lot more light than what can be captured, of course, by a pinhole, and then focuses all that light into a single point on the image plane. Light from other parts of the camera would also be gathered and focused to other points on the image plane. The result is a brighter and less noisy focused image. So you can see here how we're able to get around the problem of the pinhole camera, where only a little bit of light goes in the pinhole. Now, lens systems do not focus all the light from everywhere in the real world. The lens design restricts them to focusing light only from points that lie within the range of Z depth from the lens. The center of this range, where focus is sharpest, is called the focal plane, and the range of depth for which focus remains sharp enough is called the depth of field. The larger the lens opening, the smaller the depth of field. Now, the geometric effects of perspective anyway are not always fixed. For example, the windows on a building from the street will look much more than one like nearby. Two windows that are next to each other will have about the same size, even though one is slightly further away. So we have the option to handle the windows with a simplified model that's called scaled orthographic projection. So it handles the windows with a simplified model rather than perspective projection. So the depth of all points on an object fall within the range Z0 plus minus delta Z, with delta Z much smaller than Z0. And the perspective scaling factor can be approximated by a constant S equal F over Z0. The equations for projection from scene coordinates x, y, z, where the image plane becomes then just x equal sx and y equal s1, where s is our constant scaling factor. So by using this approach, foreshortening still occurs in the scaled orthographic projection model because it's caused by the object tilting away from the view. Now the brightness of a pixel in the image is a function of the brightness of the surface patch in the scene that projects to the pixel. The ambiguity occurs. So for modern cameras, for example, this function is linear for average intensity of light, but becomes very nonlinear if we are in a dark environment or a very bright environment. So Here we use the linear model just because it's much easier. Image brightness then is a strong cue to both the shape and the identity of object. Okay, so this ambiguity occurs because there are three factors that contribute to the amount of light that comes in from a given object. First, you have the overall intensity of ambient light. Next, we have whether the point is facing the light or is in the shadow. And finally, the amount of light reflected from the point. So most surfaces reflect light by a process called diffuse reflection. So diffuse reflection scatters light evenly across the directions, leaving the surface. So the brightness of a diffuse surface doesn't depend on the viewing direction. Now, another type of reflection is called specular reflection. In this case, incoming light leaves the surface in a bunch of direction that is determined by the direction the light is coming from. Okay, so it's not uniform across all directions. It's more focused in specific directions based on where is the light coming from. In this case, the flow of directions is very narrow, which is why you can resolve different objects in mirrors. Now, illumination ray all travel territory in one direction. Obviously, behavior is a distance from light source. So, the main source of illumination outside of the sun is the sun, sorry, whose rays all travel parallel to one another in a known direction because it's so far away. So essentially, we model this behavior with what's called a distant point light source. And this is the most important model of light. And it's quite effective for indoor scenes as well as outdoor scenes. So this photo here shows, for example, a variety of illumination. So you can see that there are peculiarities on the stems and the floors. While the onions and carrots are bright, diffuse surfaces because they face the light direction. The shadows appear at surface points that can't see the light source at all. And inside the pot are some dark diffuse surfaces where the light strikes and it projects at time. Okay, there are also some shadows inside the pot. So when two surface patches are illuminated by a distant point source, like the sun model which I discussed, in that case the rays are shown as light arrows here. So patch A is tilted away from the source. Collects less information. However, patch B facing the source. Here collects more. So this will be our model for illumination. Next, we're going to talk about the color aspect of an image. So most humans have three types of color sensitive receptors. Okay, so because there's three, then we call it the principle of trichromacy. Okay. This idea was first proposed in 1802 And it proposes that you have the format the visual appearance of any spectral energy density, no matter how complex it is, by mixing appropriate amounts of just three primary points. Okay, so primaries are colored, light sources chosen, so that no mixture of any two will match the shape. That's how we define primary colors. So common choice for the primary colors we're familiar with is the red, green, and blue, which is RGB system. Although a given colored object may have many component frequencies of light, we can match the color by mixing just the three primary. And the proportion of each primary color is typically known to generate any new color, which means that we can represent color images with just three features, right? Three numbers for each pixel, which are the RGB values. So for most computer vision applications, we use the three different numbers, RGB numbers, and calculate the intensity or represent a specific pixel with the intensity of each of the three colors, essentially. Yeah. So this model then will be able to predict the color, the different color distribution in different lights based on the intensity of each one of the RGB component. Okay. So this effect here, or this ability, is called color constancy, okay, which we're able to estimate the color the surface would have under white light, and also ignore the effects of different colored lights. So now we have all the components needed to develop our vision models. We represent colors using three numbers at each pixel, which each number will represent intensity, which itself depends on where the light is coming from, how the surfaces are oriented relative to the light, and we know exactly how to create this model image. So the next step then is to extract simple image features, or look at what are the most important features to represent an image. Are we going to just represent every pixel in the image, or are we going to start with maybe the edges of the objects and then going into capture another feature from the image? So let's